Today we are going to start bilinear or linear fractional transformation, and the definition for this kind of transformation is the transformation Tz defined by W equal to Tz, that is equal to Az plus B over Cz plus D, where A, B, C, D, these are the complex constants, with the condition A multiplying with D, that is the coefficient of Z in the numerator, that is multiplied with the complex constant in the denominator, that is AD, and then taking its difference with BC, which is the complex constant in the numerator, that is multiplied with the coefficient of Z in the denominator, that is C. So multiplying B with this C. So AD minus BC is not equal to 0. This is the condition for the bilinear transformation. So such kind of transformation is a bilinear transformation, right? Second is determinant of this transformation. What is the determinant of this transformation? The determinant is the constant AD minus BC. This is the determinant of the transformation. Whatever you are getting AD minus BC as a constant, that constant is the determinant of this transformation. Then is when this transformation is normalized, if this constant AD minus BC, when it becomes 1, then we say that this bilinear transformation is said to be normalized. And from this one, if I take Cz plus D to the other side and multiply this with W, I get CWZ plus DW is equal to AZ plus B. And let's also take this AZ plus B to the other side. Then we get, from one we can write CWZ plus DW minus AZ minus B is equal to 0. So it is evident that this is linear in both Z and W. So that is why it is called a bilinear transformation. BT is for bilinear transformation, and as it is linear in both Z and W, it is also called Mobius transformation. So such kind of transformation is also called Mobius transformation. Next is inverse transformation. Inverse, just writing Z in terms of W, right? Okay. What is W? W is Tz is equal to Az plus B over Cz plus D. So writing Z in terms of W, we can write this as negative dW plus B over CW minus A. And that is also equal to writing this as T inverse W. So this T will go to the other side as the inverse. So Z is equal to T inverse W, that is negative dW plus B over CW minus A. This is your inverse transformation. So Z is equal to T inverse W, that is equal to negative dW plus B over CW minus A. If you remember, the determinant of the bilinear transformation W, that is Tz, that is A multiplying with this D and then taking its difference with B multiplying with C, that is AD minus BC. So now in case of inverse transformation, what is the determinant for this transformation? That is negative D multiplying with negative A, that is AD, and then its difference with B multiplying with C, that is BC. So again we get the determinant as AD minus BC. So determinant is negative D multiplying with negative A minus B into C, that is equal to AD minus BC, which is same as that of the bilinear transformation. So the determinant of the bilinear transformation and inverse transformation is same, that is AD minus BC, right? Okay, some of the notes are written over here. Let's read them. The transformation T associates unique point of W plane to each point of Z plane except, yes, except Z equal to negative D over C. So negative D over C, where C should not be equal to 0. And similarly also inverse transformation T inverse associates unique point of Z plane to each point of W plane except, what is the inverse transformation? This. So except where the denominator of this inverse transformation becomes 0. So except at the point W equal to A over C. So except W equal to A over C where C is non-zero. So Z equal to negative D over C and W equal to A over C. These are the exceptional points. So next is exceptional points. The points where the denominator becomes 0 for the transformations. So for the bilinear transformation, the exceptional point is Z equal to negative D over C. And when the denominator becomes 0 for the bilinear transformation, this point, exceptional point, mapped into the point W equal to infinity, right? Similarly, for the inverse transformation, the exceptional point is W equal to A over C. And we can write that this W equal to A over C mapped into the point Z equal to infinity. So from here we can say that every bilinear transformation sets up a one-to-one correspondence between all points of the closed Z plane and the closed W plane. So if complex plane Z plane and W plane is closed, including the point infinity, then every bilinear transformation sets up one-to-one correspondence between all the points of the closed Z plane to closed W plane, right? 7th, what is the essential condition for bilinear transformation to set up one-to-one correspondence between closed complex plane? So that essential condition is AD minus BC should not be equal to 0. This is the condition for which bilinear transformation sets up the one-to-one correspondence between the complex planes. What happens if this AD minus BC becomes 0? Then for the transformation for W equal to AZ plus B over CZ plus D, this becomes constant or meaningless. Let's take 2 points W1 and W2 that are associated with the points Z1 and Z2 respectively. And what is W1 then? Just put W1 instead of W and put Z1 instead of Z. Over here we get the value of W1 as AZ1 plus B over CZ1 plus D, and W2 will become AZ2 plus B over CZ2 plus D. Then if I take their difference, I get AZ2 plus B over CZ2 plus D minus AZ1 plus B over CZ1 plus D. And after taking the LCM and managing the terms containing Z1 and Z2, we will get AD minus BC into Z2 minus Z1 over AZ1 plus D into CZ2 plus D, right? So hence W2 minus W1 is equal to 0 if this numerator is 0. Then only it can become 0. So this will become 0 if AD minus BC is equal to 0, which implies W1 is equal to W2, that is, W is constant if AD minus BC is equal to 0. right? So W becomes constant provided Z1 should not be equal to, yes, negative D over C, and Z2 should not be equal to negative D over C. So if AD minus BC is 0 and if either Z1 not equal to negative D over C or Z2 not equal to negative D over C, then W becomes meaningless, right? Okay. Then is the critical point. W is equal to AZ plus B over CZ plus D. Just taking the derivative with respect to Z, we get CZ plus D whole square in the denominator, and in the numerator we get, after solving the derivative, we get AD minus BC. So if Z is equal to negative D over C, then dW over dZ becomes infinity, because when Z is negative D over C, the denominator will become 0, which means dW over dZ will become infinity, right? And if Z equal to infinity, suppose here if Z is tending to infinity, then dW over dZ becomes 0. So hence Z equal to negative D over C and Z equal to infinity. These are the critical points where the conformal property does not hold. Please remember this. So note, every bilinear transformation represents a one-to-one conformal mapping of the whole closed Z plane onto the whole closed W plane.